Hi, I'm Daniel Chan from UNSW Sydney. Welcome to another adventure in pure mathematics. Today I want to talk about Hilbert reciprocity, which generalizes Gauss's quadratic law of reciprocity and features the all-important arithmetic invariant, the Brauer group. Now, Hilbert reciprocity uses the Hilbert symbol. So let's just remind ourselves some things about the Hilbert symbol. So firstly, this involves a local field. So the local fields are R, and we know a little bit about R, and the Brauer group of R, which is just Z mod 2. The only non-trivial element in there is Hamilton's quaternions. And the other local fields that you look at in this game is Q hat P, at least in this version of Hilbert reciprocity. So let's just remind ourselves about Q hat P, the p-adic rational. So what does that involve? So basically, they're just Laurent series in P. So you've got something of the form a n p to the n plus a n plus 1 p to the n plus 1 plus all the way forward. There's a dot 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 there. So it starts at some n, which is some integer, possibly negative. And these coefficients, these AIs, are just, you should think of this as like a base P expansion. So the only things that you need to use are 0 up to P minus 1. Okay. So the Hilbert symbol, A comma B P, okay, is basically something that's in the Brauer group of Q hat P. Okay, the two torsion inside there, and this two torsion is isomorphic to Z mod 2Z or plus or minus 1. So really, uh, this number is just plus or minus 1. And the key thing to remember about this is that this is a bilinear form on the multiplicative group. Okay, so you've got this A and B here, that are the inputs, and then you'll get an element which is either plus or minus 1. And the inputs A and B, they're in the multiplicative group. So we have to understand the multiplicative group of this Q hat P very well. And the first fact which we'll use is that this is easy to understand. It's just Z cross Z hat P. Okay, so let's just see how this isomorphism works. Okay, so the way I'll do it is I'll go from the right-hand side, Z cross Z hat P cross to Q hat P cross. Okay, so what does that do there? So basically what happens here is if you have an integer n, okay, and so what's Z hat P? Basically, they're just power series in P. So you're not allowing negative n's inside here. Okay, and the Z hat P, so suppose you have an element inside there. Let's call it A. This gets mapped to what? It just gets mapped to P to the N times A. Okay. So why is that? So what does it mean to be inside Z hat P cross, a unit inside Z hat P? Well, basically, it just means that when you write this p-adic rational out, and it's a p-adic integer, so you can write it as a power series. So you write it like this: a0 plus a1p to the 1 plus a2p to the 2, p squared, plus so forth. It has to be invertible when inverse a power series. And just as when can you invert a power series? Well, precisely when this first coefficient a0 does not equal 0. Okay, so when that's non-zero. Okay, so basically, what are the elements inside this Z hat cross P? So they're the power series where the constant term is non-zero. And of course, what can you say about every Laurent series in P? Well, you can pull out this first P to the N here with the first non-zero coefficient an. You can pull out that P to the N, that gives you that element here. And then what you'll get is something which is a power series with non-zero constant terms. So that's your element inside here. And that gives you the isomorphism in this fact here, like that. Okay. So remember this Hilbert symbol is a bilinear form on essentially the multiplicative group of Q hat P cross and also R. Okay, they're the local fields, R cross, but it's also trivial on squares. Okay, so we actually want to look at what is this Q hat P cross modulo squares. And that's done on the next slide. Okay, so what is this q hat p cross modulo squares? Well, we saw what this q hat p cross is isomorphic to. It's z cross z hat p cross. Okay, so of course, if you want to go modulo squares, you just have to say it's just the product of z modulo squares. So but this is written additively. So this is really just z modulo double. So that's z mod 2 cross, and then it's this modulo squares. Okay, so we've broken this down to just the p-adic units. Okay, that's what that's involved now. Okay, so I'll tell you what this equals later, but I want to sort of explain at least the answer that you get when p is odd. Okay, so p here is a prime, and the key point is that, okay, so let's try to work out what does it mean for something to be a square, okay, inside here. So firstly, elements inside here, they're just power series in p, and when you square it, of course, you get some sort of power series in p, okay. And the question is, when is such a power series like this a square? Well, the thing is that Hensel's lemma tells you how to do it, and it's very similar to what happens with just a usual power series. So if you don't know about Hensel's lemma, you can look at my video on Hensel's lemma. But if you don't want to do that right now, just remember it's very similar to the situation with power series as you see in complex variables. Okay, so the main thing is that it's quite easy to square root power series, and the only obstruction is whether you can square root this a0 mod p. Okay, if you can take the square root of a0 mod p, then you can square root this whole power series, okay, in a fairly natural sort of a way. Okay, so this a is a square if and only if to check. You don't need to look at any of the higher order terms. You just need to look at this a0. It's a square if and only if a0 is a square modulo p. So when you take all these power series, which are units, so these units in Z hat P, and you mod out by all these squares, so you can mod out by any power series such that A0 is a square. What you'll see, just with a little bit of thought, is that this is equal to what? It's just equal to the possibilities for this A0, which is F cross P, okay, modulo squares. And that's all you get. Okay, so this is something that's known. We've looked at this before. Remember this F cross P is just a cyclic group of order P minus 1. And P being odd, this is of even order. So when you go modulo squares, this is isomorphic to Z mod 2. So this second factor here is just isomorphic to Z mod 2 as well. Okay, so let's just see what we've proved here. So now we've got a good handle on what this Q hat cross P modulo squares is. It's just Z mod 2 cross Z mod 2 whenever P is odd. And you can say more. You can actually say what the generators for these product of cyclic groups are. Okay, so they come from basically, so what was the generator of the original Z? Okay, so basically, if you remember from the previous slide, it's given by this P. So where does 1, oops, sorry, let's erase that and switch to the highlighter. Where does n equals 1 get mapped to? It gets mapped to P, and if you have A is trivial here, so it's just 1, you'll just get P. Okay, so one of the generators, so the 1 here gets sent to P. So that's one of the generators on the next slide. So you have P is one of the generators, generating this copy of Z mod 2. And what about the other one? So you'll need to have some P, an element of this bit here. Okay, this bit here. And what's that equal to? So basically what you want there is you want something that's a unit modulo P. Okay, so you can pick any, so you can, for example, pick U to be some integer, which is not a multiple of P. And then what you want to generate this, remember, is it's got to be such that when you look at it inside Q hat P, so you take the base P expansion of it, and you want to make sure that this term here is not a square. So in other words, U is any non-square mod P. So that's the other generator. And there are your two generators for this uh, this abelian group of that's two torsion abelian group. Now the situation for P equals 2 is a little bit more subtle. Okay, so let me just tell you the answer. Q hat cross 2 modulo squares. So again, the prime 2 is in there. But when you compute this part here, okay, this part here, you'll find that it's a little bit bigger than just Z mod 2. So it's now two copies of Z mod 2. And they can be generated by -1 and 5. So note that these are both odd numbers, and they will generate, they will complete the set of generators for this 3 copies of Z mod 2. Okay, so let's just remind ourselves what's going on here. Okay, so why are we interested in this? So to remind ourselves, if you look at this Hilbert symbol, so you put in two elements uh, uh, in Q hat cross P, okay, but actually it's trivial on square, so you can think of this as an element of this two torsion abelian group. And as a two torsion abelian group, you can also think of it as just a vector space over the field with two elements. So you put in two elements like this, and then what happens is that it maps to the Brauer group of Q hat P, and the two torsion in there, which is by class field theory, that's a result I didn't prove, but I stated, is plus or minus 1. Okay, so that's a version for the finite primes P, and we also saw that you can have a version for the reals. Okay, and we looked at this in the previous video in this playlist, and of course for the reals, the Brauer group, the whole of the Brauer group is just plus or minus 1. Okay, so that's all we need to know about the Hilbert symbol for now. What I want to do is I want to relate this Hilbert symbol with the Legendre symbol that occurs in Gauss's quadratic law of reciprocity. And the way I want to state it is as follows. Let's just set up some notation. Okay, so normally when you write Gauss's quadratic law of reciprocity, you have two distinct odd primes, P and Q. I'm going to throw in a third one, which is also different from those two. And also appearing in Gauss's quadratic law of reciprocity is this function here. Epsilon P is going to be the following integer. Since P is odd, you can subtract 1 to get an even number and divide by 2, so it's still an integer. Okay, so it's this integer, epsilon P is an integer. Okay, so let's look at the following values of the Hilbert symbol. Okay, so firstly, what's PQP? Okay, so you have an odd prime P, and you look at the Hilbert symbol with respect to this P, and the other coordinate that you put here, variable you put here is Q as a distinct odd prime. Or this is just the Legendre symbol QP. So remember this on the left is either plus or minus 1, and I'm saying it's plus 1 precisely when Q is a square mod P, okay, and it's going to be minus 1 when it's a non-square mod P. Okay, so that's what happens for, so P here is the same as one of these here, and it's odd. So what about PQ? What happens if this prime here, down here, is the even prime too? What's PQ of that? That's going to be plus or minus 1, and how can you tell whether it's plus or minus 1? Well, it's given by this nice little function of P and Q here. It's minus 1 to the power of epsilon P times epsilon Q. And this is something that I hope you remember also occurs in Gauss's quadratic law of reciprocity. Okay, so the final thing that we want to know is what happens if you look at the Hilbert symbol, but the prime here, L, is not the even prime too, nor is it related to P or Q. In this case, the value of this Hilbert symbol is just 1. Okay, so let me just give you some words as to why this is true, some explanation of what's going on. In many ways, this is the heart of, if you prove this, you essentially prove the Gauss's quadratic law of reciprocity. So there's quite a bit of work that goes into it. Okay, so let's just look briefly as to why it's true. Okay, so let's have a look here. Let's look at part one. Okay, so what's going on there? Okay, so this is the way you should look at it. So here, um, what do you have? So what type of situation do you have? So key Q here corresponds to what? Okay, it's an integer. So firstly, if you write it out inside Q hat, so remember these are integers, so you think of them when you compute the Hilbert symbol as inside the multiplicative group of Q hat P cross, Hilbert symbol with respect to P. And Q inside here, of course, when you write down a base P expansion for that, of course, it's going to be a polynomial, and in particular power series. So this is really inside Z hat P. And since it's a distinct prime, okay, it's co-prime to P, so it's a unit. Okay, so it's Z hat cross P. And remember the value of PQ, okay, if Q is a square, mod P, then remember the value that the Hilbert symbol takes is its trivial. Okay, so we know um, if Q is a square, mod P, so in other words, this is equal to 1, then Q is an element of Z cross P squared. So that implies that PQ, this P, is equal to 1. Okay, it's trivial on squares. If you have a square either in the first variable or the second variable, it's going to be trivial. And so the only other thing that you need to know is if Q P equals minus 1, then this PQ P is equal to minus 1. And that's because, and this is where we have to use the local class field theory. When I gave you the description of the Brauer group of Q hat P, you'll note that this is the thing which generates the two torsion element, non-trivial it's the non-trivial two torsion element in um, this Brauer group. Okay, so you basically have the P here, same as that, and you need something which is a non-square modulo P inside here. That was the central simple algebra that I gave that corresponds to this element of the Brauer group. Okay, so that's essentially why you get a minus 1 there. Okay, so note that it's quite easy to sort of like work out what these values are. It looks like there are lots of values, but really at the end of the day there aren't that many possibilities because you only need to know what it is up to squares. Okay, so to evaluate these Hilbert symbols, you only need to know what it is up to squares, and this Q hat P uh, modulo squares is either the product of two cyclic groups, or at most when you have P equals 2 is the product of three cyclic groups. So you just have to look at the generators, and the generators here are firstly, in this case here, is L, or you can have something which is a non-square modulo L. Okay, so they're the possibilities. Okay, so they're the three values that we're going to need to use for the Hilbert symbol. And now we're ready to state Hilbert's wonderful generalization of Gauss's quadratic law of reciprocity. Okay, so the form that it takes here is also a formula. Okay, and what we're going to do is, unlike in the previous case of Gauss's quadratic law of reciprocity, we're going to have two non-zero rational numbers, a and b. So of course these rational numbers, you can always write down a base P expansion for them. And so in particular, these you can think of as being inside, you can map them into Q hat P cross, or think of them just as rationals, okay, inside R cross non-zero, I mean not rationals, non-zero reals rather, okay. So that means that you can consider all these Hilbert symbols A, B, P like this, okay. And what I claim is that if you range over all the primes P runs through all the finite primes, okay, so 2, 3, 5, and so forth, and also infinity, so that's the case when you look at the local field R, Okay. Firstly, you can take the infinite product of these because actually most of the time you'll get 1 and only for a finite number of cases will you get -1. And the product that you'll get here is 1. And that's uh, Hilbert's law of quadratic reciprocity. Okay, so it's a beautiful formula. And let me just see how you can relate to Gauss's law. So how does that work? So in that case, what you have is you're looking at PQ, distinct odd primes. And let's see what values occur here. Okay, so for example, one of the values is PQ infinity. Now here we're going to assume that these are greater than 0. Okay, the formula works if they're negative as well and gives you interesting things. But in this case, since they're both positive, this is equal to 1. So there's a 1 there. Okay, so what other values do you have to look at? So what are the values which are possibly not 1? So the formula, theorem implies, well, firstly, you have PQ2, that's a possibility. Okay, PQP, that's another factor in there, and there's PQQ that's in there. And the product of these and all the other ones is equal to 1. But all the other ones are for sure equal to 1. So if you have a prime, an odd prime, which is not P or Q, then those Hilbert symbols are all equal to 1. So this is this part 3 here. Okay. And then also the infinite prime here, we just saw that we get PQ equals 1. The Hilbert symbol is 1. So basically you have a product of 3 things. And let's see what those 3 things are. So from the previous slide, this one here is just -1 to the epsilon P times epsilon Q. This one here, PQP, I showed you what the value of that is. That's just the Legendre symbol QP. And this one here, remember this Hilbert symbol is symmetric. So this is also QPQ. So at the end of the day, you just swap the roles of P and Q, and you get PQ. And here we see that we recover Gauss's quadratic law of reciprocity. Okay, so how is this a generalization of Gauss's quadratic law of reciprocity? So it's a generalization in a couple of different ways. So the mild way that it's generalization, okay, is that firstly, you're not just looking at odd primes here. You can look at certainly any integer that you like. Okay, any integer and even any rational number, you can extend it to that setting. Extending to from primes to integers and rational numbers is not a big deal because it's bilinear in each variable. So uh, that's in many ways just a minor point. Okay. But one of the things that you do find is that you can put in P and Q to be equal to 2 or -1 as well, and you'll get some extra results. Okay, so often they're called addenda to Gauss's original quadratic law of reciprocity. Okay, but the main part in this form, as I formulated here, it's essentially the same as Gauss's quadratic law of reciprocity. So the beauty of this formula is the fact that it looks really nice. So in particular, it's easy to generalize this. Okay, so let me just state this here. It generalizes to any number field. Okay, so this is the setup. So you can replace Q with any finite extension of Q, and then you still get a similar looking formula to this. Okay, so you'll have to understand what's meant by a prime. Okay, so firstly you have primes in the rings of integers, so you can look at that, and you'll also have infinite primes, and that's a little bit more subtle. So you can do this various ways. You can look at it, for example, in ways that you can complete the field. Okay, and then you can look at elements of the Brauer groups. Okay, and again you have a similar story. So the two torsion in the Brauer group is always the cyclic group Z mod 2. And so you can define the Hilbert symbol, and that's always going to be a value ±1. And then this formula that Hilbert came up with, it holds in this context as well. And in this way, you can generalize Gauss's quadratic law of reciprocity to any number field. I hope you enjoyed this adventure in pure mathematics.